there?
Yes, okay. I'm on.
Rosmi?
Yes.
It's already 6 o'clock. We can start. Other people will join. Yeah.
There are no stars. The one.
Yeah. Okay.
There is
Rosmi,
no.
go ahead. Go.
The one creative and innovative ideas.
I cannot hear you. Yeah. Go ahead. Go ahead.
Because of the day, Mr. Ajit K. Kumar, renowned guest, and all the participants. Good evening to everyone here. I'm Rosmi Johnson. I'm honored to welcome you all to the 8th Indian Society Weekly Webinar Series of my experience with the heavy haul propulsion. Jointly organized by IEEE Kerala Section, the Institution of Engineers, Kerala State Center, Computer Society of India, Trivandrum Chapter, Project Management Institute, Kerala Chapter, Internet Society, Trivandrum Chapter, Locomotive Foundation Trust, Trivandrum, Life Member Affinity Group, IEEE Kerala Section, IEEE Engineering in Medicine and Biology, Kerala Chapter, the Institute of Electronics and Telecommunication Engineering. Before beginning our section, I would like to let you all know few of the program protocol. All participants are requested to put your Zoom signals of that of the registered name of the event. All participants except for speakers are requested to mute their audio and turn off their videos throughout the section. Participants can raise their queries through the chat window at any time through the section, which will be later addressed in our Q&A section. Kindly fill up the feedback form, which will be shared at the end of the webinar, and those who want certificate may indicate on the feedback form. Heavy haul propulsion systems used in freight applications like locomotive and of high vehicles have evolved significantly in the last few decades. To ignite us on the scene through the experience, we have the distinguished speaker of the day, Mr. Ajit K. Kumar, Vice President Technology Innovation in Wabtec US. Being delightful, I would like to call upon Mr. Anlan J. Sejin to deliver a welcome address. Please do the honors.
Good evening, ladies and gentlemen. It's my immense pleasure to represent IEEE family and to welcome each and every one of you to the 83rd talk of Indus Society Weekly Webinar Series talk. First of all, let me appreciate the effort of Harindra Alsa, co-volunteer and professional of Kerala section, who are supporting this event to fabricate it as a huge success for the past 82 talks, bringing out the best profiles and presentation to the virtual room. Moving on my assigned duty today, I am so delighted to introduce our speaker, Mr. Ajit K. Kumar, Vice President Technology Innovation in Wabtec US, sharing his experience with heavy haul propulsion. We welcome you, sir.
Thank you.
Next, I welcome Harindra Alsa, the chairperson of Indus Society, the lead of IWWS, this auspicious evening. We welcome you, sir. Next, I would like to extend my warm welcome to the volunteers of today's session.
An introduction concerning the renowned speaker. We have Ms. Hannah Ansa. Over to you.
Thank you, Rosmi. It's my esteemed privilege to welcome our eminent speaker to this 83rd Indian Society Weekly Webinar Series. He is none other than Ajit K. Kumar, the Vice President, Technology Innovation in Wabtec US. Sticking to his profile, Ajit K. Kumar was graduated from Trivandrum Engineering College in 1972 with a bachelor's degree in electrical engineering, ranking first in Kerala University. After graduation, he worked as a lecturer in CET until 1973. He worked for a few months as a technical officer in the Syndicate Bank and joined the R&D of Keltron. In 1977, he got a master's degree from Stanford University in electrical engineering using a Rotary Foundation scholarship awarded through Trivandrum Rotary Club. He has worked at General Electric Company in its transportation division from 1977 until 2019. He currently holds the position of Vice President, Technology Innovation in Babcock, which acquired GE Transportation in 2019. In addition, he holds a master's degree in engineering and an MBA both from Gannon University, USA. During his work at GE and WAPAC, he has been instrumental in the development of propulsion systems for transit vehicles, freight locomotives, passenger locomotives, and off-highway vehicles. Due to this effort, most of the freight railroads have switched from traditional DC propulsion systems to AC propulsion systems. Ajit sir further has contributed to the trip optimizer systems and has advanced technology for fuel savings, dealing with auto propulsion, braking, independent distributed power, and air brake advisement, which eliminates 5 lakh tons of carbon dioxide emissions per year. His latest effort has produced the world's first battery-only powered freight locomotive with 2.4 megawatt capacity and is running since December 2020. He continues to lead a team on a second generation FLX drive locomotive that will have more than 6 megawatt capacity and reduce fuel consumption and carbon emission up to 30%. Mr. Ajit is a recipient of the GE Edison Award and GE Dushman Award. This year, he has been selected as the Engineer of the Year by the Society of Asian Scientists and Engineers. In 2015, he became the most decorated patent holder among over 3 lakh GE employees worldwide and was recognized by GE Chief Executive Jeff Immelt for that distinction at a special company function. He holds 354 US patents and around 1,000 international patents, including India, and has published many articles. Ajit sir used his Edison Award to fund a scholarship for CET graduates to study and get a master's degree in engineering in USA. So it's my immense pleasure to welcome this warrior to this 83rd Indus Society weekly webinar series. Sir, the platform is all yours.
Okay, thank you for the kind introduction. Can I share my screen? Okay.
Yeah, please. You may go ahead. Yeah, that's fine.
Okay. Thanks for the kind introduction. I'm going to talk about my experiences with the propulsion system. I had talked a little bit about it a few months back to a similar group in India. So for some of you, it may be a repeat. So I want to talk a little bit of the background, which you already know. But the one I want to talk about is what I did was I got my bachelor's degree from CET in 72, and it was heavily focused on electrical power. So like electric machines, transformers, those kind of things. And electronics was not advanced at that time. I went to Stanford. There, it was mostly computers and computer programming and algorithms, integrated circuits, those kind of background. So I tried to combine the two and look for an opportunity and found it in GE. And GE Transportation makes mostly freight locomotives, as what is shown in the right-hand side, and make mining vehicle propulsion. We don't make the mining vehicle itself, just the propulsion of it is what GE Transportation makes. So I got into that and I tried to combine the two together, mostly to improve the performance and fuel efficiency. These trains, unlike most of the passenger trains, are owned by private railroads to haul heavy haul freight like ore, iron ore, copper, very, very heavy freight. That's where the application is. And so mostly it's going to be funded by private institutions which look for saving money. Okay, just a brief background on the history of the company. It was started by Thomas Edison more than 100 years back. And this is one of his patents and was on railroad equipment. You can see it's a lot different from what we know of locomotives today. And GE Transportation made diesel locomotives for many, many years and electric locomotives for many, many years. And when it started out with, it was a very small locomotive. So in the 100 years, it has changed significantly from 1908, if you compare to 2015. The weight has gone up. Most of the locomotives in US, Brazil, Australia, where it's used for heavy haul, is a 33 ton per axle. Compared to that, you will see in India, it'll be around 20, 25. 25 is maximum you'll see around the world. But most of the heavy haul is 33. So it's meant for going at low speed, typically, and hauling heavy haul. Heavy 15,000, 20,000, up to 40,000 ton trains. And the speed is limited. Typically 70 is high speed actually for a freight locomotive. Okay, GE Transportation makes locomotives of different sizes. You can see the smallest one is on the right-hand side. It's used in New York City. It needs to go through the tunnels of New York City. That's why it's so small. And the one on the left is the one which is used for freight applications. And India locomotive will fit somewhere in between. Okay, here is the India locomotive, the one we designed, and we are supplying about 1,000 of them made in Bihar. The first few are made in Erie, Pennsylvania, and the rest of it will be made in Bihar. Okay, now if we compare the railroad applications, this is the tonnage hauled by, let's say if you have a mile of track, a kilometer of track, here is the billions of tons per kilometer. India is somewhere in the 600. So it hauls 600 tons for every kilometer per year. Compared to that, it's about 4 or 5 times when you apply heavy haul applications. So the technology used is a lot different from electric locomotives, which are used in passenger application, to diesel in heavy haul freight. And during the last 30, 40 years, the fuel efficiency has improved significantly, almost 2 to 1, due to lots of technologies which has been introduced, and some of which I am part of it. And I'll talk about a few of them. And same way that the revenue or ton miles or the amount of freight you can pull through a given track has gone up significantly, about 2-3 times what it used to be in the last 30, 40 years. And for that to happen, there are many things need to be looked at. You have to look at it from the individual locomotive, which is what does the engine do? What does the propulsion system do? That's where I started out with. Then I started looking at, in a typical train, there are multiple locomotives in the train. So what can when you have 2 or 3 locomotives in a train, you can optimize things. And the last one I worked on, the full train itself. The train is not a locomotive, so it need to go from point A to B. So what does it take to go from point A to B? That's so far I haven't gone into the railroad network management itself. That has to do with how to dispatch trains, which trains should take priority, where should it meet and pass, those kind of things I haven't looked into. So the first 3 optimizations where I concentrated mostly. So if you take a look at a locomotive or a train, typical train is 2,000 to 45,000 ton. Typical train, which I'm used to. The biggest train is about 99,000 tons, which is a test train. It's not a real operating train. A typical train in US consists of 3 to 5 locomotives. The maximum is 7. And trains are 1 to 3 kilometers long. And this is a key metric, the next one I talk about, 0.3 to 3 kilowatt per ton. What that means is if you had a car and you had a 1-ton car, that means you're allowed to use 300 watt drill to drive that car. So that's the amount of power the train has per ton, which is very small. And that's the main reason why it takes forever to accelerate a heavy haul train and to slow down a heavy haul train. In addition to that, there's a lot of terrain related issues. Like you can see here is an undulating terrain, tunnels, curved terrain. In a tunnel, for example, like this one, the temperature goes as high as 140, 150 degrees centigrade. So the train need to operate through there. These trains or these locomotives, the force of a locomotive is about 3 to 3.5 times of a GE jet engine at starting. When you go to high speed, it doesn't have that kind of force, but at starting, it's about 3 times that of a jet engine. And you can compare, I'm comparing it with the biggest passenger car. You can find an SUV, and you can look at the comparisons. It's about the size of an 80 or the weight of an 80 full-size SUVs. A typical locomotive consists of an engine, which is generally at the middle due to the weight distribution. So generally at the engine, the operator, of course, at the front, with lots of equipment in front for crashworthiness. So, and to make sure that when a train hits something, the train will get on top of it and not go under it. So there is lots of equipment in here to make sure that the train does not get crushed by something else. And of course, radiators and controls. So I won't go through all of it, but some of the things from an electronics perspective, a typical locomotive today has about 12 to 15 antennas for GPS, satellite communications, radios, cell phones, Wi-Fi. So a locomotive is always in communication with the central dispatch. For example, most of GE locomotives are in communication with the GE Remote Monitoring and Diagnostic Center to continuously monitor its health. And about 50 computers are there, which is unbelievable. There are 50 computers running different things from traction. That's where my expertise is in traction and traction mostly. And the constraint is set by the tradition, means the distance between the rail is already fixed. Most of the places, the tunnels are all fixed, so therefore you cannot increase the size of a locomotive. So the space for different countries is limited. Okay, I'm going to skip some of the charts, but when I started working on it, most of the locomotives use, or almost all of it, except passenger locomotives and electric locomotives, used DC propulsion equipment, and it had lots of issues. One of them is the failures due to water ingestion or snow. The other one is it takes up, the commutators took a lot of space, and the most premium space in a locomotive is between the wheels because the track gauge is already fixed. So my first attempt was to take the commutator out of there and move it upstairs above the platform to get more space for power. And that is what shown here. It's an AC propulsion, which takes the power from the engine through an alternator, through a diode rectifier, through 6 traction inverters to each of the traction motors. So now the commutator is gone from the underneath the platform to above the platform. You have a little more space for the traction motor, which means you can put more torque or more tractive effort or more horsepower into the rail. So that's where I concentrate most of the time from 77 to 1990s. So about 20 years I worked on it to get it to this shape. So there are many things I can talk about, but some of them I'll talk to a couple of examples, like the hybridization or energy recovery. Some of the examples of how to increase the pulling power of the locomotive, trip optimizer, which was meant for fuel efficiency, stuff like that. So a typical train consumes about 4,000, a typical locomotive consumes about 4,000 liters per day, or a train will consume about 20,000 liters a day. And US railroads consumes about 14 billion liters per year. So these are big numbers. So any small improvement in fuel efficiency has a significant benefit to the bottom line of these railroads. So the first step was to increase the pulling capability. If you can increase the pulling capability, that means you can add more cars to the train, which means more money to the railroad. We have all seen an ideal friction coefficient, the rolling friction and static friction. The static friction of steel on steel is about 0.65, but a train does not pull that kind, it does not see that kind of friction due to various factors. Most of them you cannot control. You means the manufacturer of the locomotive cannot control. It's all due to material, geometry, curvature of the railroad itself. And there's always weather-related issues, moisture and ice, contamination, corrosion, leaves, oil, millipedes. So during millipede infestation, it's slick. Most of the railroads are extremely slick. It doesn't have any adhesion left. And how the railroads how they practice their dispatch. So whether they put all the locomotives in the front, the middle, somewhere in between. So the things which you can control are the ones on the top. So I'll talk couple of things, but I won't go over all of it. So by the time that 65% adhesion, if you can get 35, that'll be extremely good. And when we started looking at it, once the computers came into existence, then you can look at the creep. Creep is the wheel goes at a slightly higher speed than the locomotive goes at. And very, very slight increase in speed is all it takes to convert from this is static friction to rolling friction. So you lose significant amount if you increase the speed by even a few milli RPM. So with the computers, you can look at the speed of the locomotive and compare with the speed of the wheel and look at that minute difference in the speed difference. And that difference is what's used to control it to the peak of the force, friction force. In school, we have studied static friction and rolling friction, but it is classified as stationary or moving. But in reality, when the locomotive itself is moving, that analogy doesn't work. So we look at a creep, which if you are in the 1 or 2% creep at high adhesion, you lost the game. So the objective is to find out what speed the wheel should be run at for a given locomotive speed. So if the locomotive is going at 20 kilometers per hour, the wheel should be going at, say, 20.1. And what my control does is slightly adjust that speed. So every 3 milliseconds, it looks at what the speed increases, what the torque increases, if they are in the right direction. So if it's increasing, continue to increase. If it starts decreasing, bring it back. So that's the whole adhesion game. So now almost every railroad uses that technique to maximize torque. And we are in the process of going even further because the suspension of the wheel, even though we may increase torque due to the spring and mass, it doesn't exactly represent the speed of the wheel. So there are techniques being incorporated using Kalman filters and observers to look at about 300 characteristics per second on the wheel itself, and to minutely control the speed of the creep of the wheel to increase the adhesion. So right now we make about 93% of the available adhesion under the rail. So there is 7% more left to get. The most important information you need to know for this control is the speed of the wheel, speed of the locomotive itself. And there are a lot of times that is the most difficult thing to do. GPS, if you think of GPS never tells you what the speed of anything is. It always tells you what the speed used to be about a few seconds back. That's too late. So most of the equipment do not supply the speed at the current state. There's always a transport lag. We have looked at inertial navigation systems, which are used in missiles and other applications, none of them provide you the speed at this instant in time. So the technique which is used now is that periodically one of the wheels tractive effort is dropped, and we look at the characteristic of the wheel slip characteristics to figure out the locomotive speed. And since there is no operator on these locomotives, it is crucial that we know the speed exactly. Here is an example of where in one of the locomotives, it didn't know the speed. So it thought the speed was, the locomotive was moving, applied adhesion, and you can see the shape of the rail after that. Okay, I'll talk about, that's difficult to condensate all the processes I use. So I'll take two examples. This is the first one. And in some of them I have listed the patent number. So you can go and study it if anybody is interested. And most of them, the ones I'm going to talk about are simple, almost anybody can understand. The first one, as I said, is a 200-year-old problem. And there, if it's a problem, it's an opportunity also. So the problem is how to improve the friction between the wheel and the rail. And if you look at, for example, when you want to paint something or clean some surface before painting, that's where I started with. If you look at it, people do sandblasting before painting to clean the surface. So the question was, why couldn't I sandblast the rail before the locomotive gets there? So we looked at sand, we looked at silica. So we took silica and pumped it at 200 kilometers per hour to the rail, just at the wheel rail interface with a nozzle like this, injected silica to improve the adhesion. We looked at walnut shells. So put lots of walnut shells and pumped it in between. Glass beads. Today, most railroads use sand. The sand has an issue in the sense that if you ingest it, you can cause silicosis. So we are in the process of removing most of the sand, as much sand as possible, but till most railroads consume a huge amount of sand to improve adhesion. Those are all complex designs. So finally, by luck, this is what came out. So we were trying to ingest high-speed sand into the rail. And during the testing, we ran out of sand, but still the adhesion improved. It has to do with the high-speed compressed air. So that's what the technique ended up to be. So we ingest high-velocity compressed air into the wheel rail interface, and it increased the adhesion significantly. So each of the railroad could add many, many cars due to that one little gadget. It has lots of technical issues also, questions like how much pressure, how high a velocity, where should the air be angled at. Those are all concepts and techniques which were perfected to increase that kind of capability. It was just by luck that this happened, mostly because we ran out of sand. So it's a simple technique, and the technology is in the how much air to apply, how high a force to apply, how much flow to apply, what angle, what height, what should be the nozzle geometry, whether it should be heated air and stuff like that. And there are safety issues also. These are very, very extremely high velocity air coming in. So if you angle it the wrong direction and if somebody parked a car next to it, any particles or any stone in that railroad which will be thrown out at very high velocity. So that's the reason why it's angled inwards, so that it doesn't get. In some countries, like in Australia, they have used this for millipede blasting. What that means is during certain millipede infestation times, there'll be lots of millipedes on it. So the air will throw them out of the track. So I want to talk about one which failed. So the first one I just showed was a product or a concept which succeeded. There is another one which failed. So the concept was to improve the pulling power of the train. One option, as I talked about, is to increase the adhesion in the front of the train. The other one is to decrease the adhesion back of the train so the cars don't need too much friction. And so there you put sand or compressed air in the front and put drops of water or ethylene glycol or any friction reducing material which will evaporate behind the locomotive so that the pulling required for each car is reduced. That did not succeed for commercial reasons. Technically it worked, but for commercial reasons it wouldn't, because you need to make sure that whatever we put in evaporates before the next train comes. Otherwise, it loses its adhesion. So for that reasons and the amount of this material to be dispatched, it didn't succeed. Another simple concept which succeeded quite well is the cost of the locomotive also matters for most of the railroads for their return on investments. So one of the concepts was to remove out of the 6 wheels, can I remove 2 of the traction motors or 2 of the propulsion systems and make the same amount of power? As we said, adhesion is the reason why the trains don't have enough pulling capability. So adhesion, the first concept in adhesion is the weight you apply on the track. So question was, can I increase the weight of the axle when I wanted it? And that's the concept. So I'll show you the. So if I can crank this axle up and compress the spring, that means the unpowered axle's weight will be transferred to the powered axles. It's a very simple equipment, and it made enough tractive effort to sell about 1,500 locomotives. So I'm going to change subjects slightly, go from locomotives to trucks. So we talked about a locomotive, it's about 3.5 times the pulling capability of a jet engine. Now, if you look at a truck, here is a car wheel. A typical truck is that size, so it's 4 meters outer diameter. Some of them are even higher, but compared to a car, it's a big truck. So the type of trucks which I work on, propulsion, is 150 ton to 400 ton trucks. They look like these. That has the pulling capability of 5 locomotives and the volume of about 2.5 locomotives. It's typically a 1,000,000 pounds or a 500,000 kilograms of weight is what is on a truck. Generally, they cannot go through any roads. It's shipped in parts, then assembled at the mine itself. So a few examples, if you want to. It's a payload is a Boeing 747's worth of payload, or it's like a 60 elephants. Here is me standing in front of the truck. You can see the height difference, and here is where the operator sits, and that's where the payload is. It's about 700,000 kilograms to a 2-story house. I'll show you a video. I don't know if it'll work or not. If it works, we'll So I don't know if you could hear or not. There are hundreds of them right now in the world. When the video was taken, there were a few. It's fun to drive. And here is a mine. This is the largest mine in Utah. And you can see, if you see the truck, the big truck is right here. And when you go to a mine, there are a lot of, what should say, safety concerns. They overloaded. They put hot material on the trucks, so they should be able to operate from minus 55 to plus 55 C with many, many toxic substances around it. Okay, last year's my effort has been to increase the capability of pulling heavier or higher productivity. In a mine, the productivity is measured in terms of how many tons of ore can I move through that little road. The little road is not a little, but 2 trucks will fit. So how can I increase the tonnage being hauled through that road? The issue is going to be always the diesel engine, which is on board, is the issue. So the concept is to electrify the grade, the constant grade portion. There's always, the mine is always moving, because as you dig and get ore, the head moves further out. So the mine is never stationary, it keeps moving. But still, there's a significant portion of the road which doesn't move. So that section, where there's a big grade, can I electrify it, which means you can increase the speed of the vehicle, which means you can get more productivity. So a few weeks back, we had the first truck running in Finland. It's a platinum platinum mine. And here is what it looks like. It uses 2 pantographs because these are rubber-tired vehicles, and you cannot apply single pantograph, and you cannot apply 25 kV kind of voltages. So you have to find the right voltage, a couple of pantographs. And so when you get to the big hill, this truck will connect to the pantograph, to the catenary, and run. These equipments are not small. These are 500 kilogram pantographs. So this has started running starting last month, about a month ago. So the productivity of that mine is going to go up significantly, because you can go through that grade at about twice the speed. Going to switch subjects again. It's not the locomotive or the truck that matters, it's a train that matters, or the whole conveyor belt that matters. So the objective is to move freight from point A to B, the least amount of fuel or least amount of energy consumed. So I started working on what hybrid cars were coming out in 1999. So I said, okay, I could do the same thing. A train like this produces about 50 megawatts of power during braking. So that's generally wasted either as heat in the locomotive or heat in the wheels. So if you can even capture a small, minute fraction of it, that's a significant fuel reduction. So that's what I started working on it, but it didn't succeed. It finally ended up in a product called Trip Optimizer. So here the thinking is, I want to go from point A to B. What can I do? So this failed battery development led to TO. I'm not going to go through this whole concept. This is the second idea I was going to talk to you. Here is the patent number. Anybody who wants to read can read it. So the physics is, I want to minimize fuel subject to certain conditions and execute that plan. Generate a plan on board, then execute to that plan. And that made a significant reduction in fuel, about 10% fuel reduction. So there are many algorithms which run on that locomotive continuously every second it calculates what the forces, entire forces on the train is, what tractive effort should be applied by each of the locomotives. So for example, in a train, typically the front of the train, the locomotives may be in motoring, the middle may be in braking, and the back may be in motoring. You'll see many times that the operators have a hard time controlling it because this locomotive may be a kilometer away, this may be 2-3 kilometers away. So you need, depending on the terrain, the operator need to remember what did he pass about a kilometer back, was it going up or down, and what's the tonnage of the cars. Based on that, they need to run different operations at different positions on the train. And so nowadays on these kind of trains, when the operator comes and pushes a button, and the railroad will transmit to GE what kind of material is being hauled, what's the weight, tonnage, length, and we'll compute a best profile to run from point A to B and execute to that plan. And it's used in many, many countries right now. Something like 10,000 systems were sold worldwide. I don't think it's running in India, and I don't think it is running. And saves a significant amount of fuel and therefore reduces the emissions. There's a lot longer way to go, but that's what we have right now. The last subject I want to talk about is energy storage. That's I started out with using NiCad batteries. That was the big thing at that time, 2002. Did not work, mostly because even today, the batteries are not economically suitable. It does not save enough money to warrant the investment. NiCad was at that time the leading technology. Few years later, it became nickel metal hydride. Then a little later, it became sodium nickel chloride. Now it's lithium ion. Lithium ion is the leading battery. Even within lithium ion, there are many, many different techniques. Cobalt oxide, manganese altite, titanate, different, right? The current NMC is the current leading lithium ion candidate. The other one is LFP, lithium ion phosphate. Lithium ion phosphate is used typically in low energy applications or in cheaper electric cars. NMC, nickel manganese cobalt, is used in high performance cars where you need a larger energy storage. So we started out with NMC batteries. So these are our batteries, big batteries, put 24,000 kilowatts. And here is what the train looks like, or inside the train. These are all batteries. This is the first 100% battery operated train, freight train. And this means standing in front of it. It looks like for example, a UPS station or a server room in a computer station. And I expect within the next few years, the capacity to increase 3 to 10 times. As I said, this is a 2 megawatt hour, 2.4 megawatt hour. A typical diesel tank stores about 75 megawatt hours of energy. That means this is a very, very small amount of energy, even though it consumes almost all the space on the locomotive. So the battery technology need to go quite a bit higher for it to compete with diesel. But however, that's the first locomotive which ran successfully. And those who are interested in it, you can see that about a few months back, Roy Hill ordered the next generation battery-only locomotive. This is going to be 7 megawatt hours, about 3 times more capability than the one we just saw. And then last week, I think, CN ordered the second one. I expect within the next 1 or 2 years, it's going to be $1 billion business, or about 10,000 crore rupees annual sales of this locomotive. So here is a peek at it. I cannot show all the details, but I can show you some of it. This much is a battery. Large of batteries, 7 megawatt hours worth of batteries. And you probably know the issues with lithium ion catching fire. It's called thermal runaway event. So there are many techniques have been used to minimize the effect of a thermal runaway. So it's going to happen because the chemistry of the lithium ion NMC is such that if there's a cell failure, it's going to go to thermal runaway. The objective of my design is to make sure that if a cell goes to thermal runaway, the next cell does not catch fire. Most likely it will be successful. We'll know in a few years. And we are in the process of looking at what can be done to increase that power even higher. Not power, energy even higher. So what do I see in the future? That's where I'll stop. One of the things we are looking into is hydrogen, clean hydrogen fuel cells. So we are in the process of, you've probably seen it in news, we are in the process of making clean hydrogen freight trains, but it's at least 20 years away in my perspective. This is the first prototype, which will be used next year. The other thing is autonomous vehicle operations. So here is an example of a inspection vehicle or a brake release vehicle. It's an autonomous brake release vehicle. That's a human going in, releasing the brakes. This robot, it's to slow down 6-to-1 just for 10 to find the release. This is the brake lever it needs to find. So we are also looking at sending a drone in front of the train. So the drones will be stationed on the roof of the locomotive. We'll charge it. There'll be a drone about a mile or two ahead of the train, inspecting the tracks. So the train can be told to stop if there is a problem. So, and then I'll come back. Another one will go and get charged. Inspection using video imaging. I want to end my talk with, I had a great time coming from looking at products at Keltron, traveling all over the world for various application. This is in Japan, in China, in Bangalore, Madhya Pradesh in India, and in England. So lots of places I have traveled for looking at railroad operations, trying to find the right equipment. So this is for Tibet, QTR Railroad. There it needs to run at 15,000 feet altitude all the time. So this locomotive can only run there. It cannot come down to sea level. And that's there. I'll end this talk. This is the first locomotive built in India with the technologies, most of the technologies I described. I'll stop here.
Please accept our sincere thanks, sir. Your section was informative, where we learned a great deal from it. We have some questions in the chat section. Sir, are we good to go with the questions? Hello, sir.
Yeah.
Are we good to go with the questions?
Sure, no problem.
The first question is, why you mentioned that inertial navigation system cannot give the instantaneous speed or velocity in the train if used.
The inertial navigation systems are generally an integrating system. So any DC bias in it produces an error in speed. So it can talk about change in speed, but cannot tell you the speed itself. For example, we use that quite a bit. We'd spend a ton of money and effort to do it. We are looking for grade changes, small grade changes. Gravitational forces itself, with the error in the processing, makes a huge drift over a period of time. So it needs some way of correcting it. I don't know if I answered it or not, but what's the next question?
Here, moving on to the next question. Can you suggest what methods are adopted in Indian railway system to reduce the friction between rail and wheels?
So in Indian Railways, the freight applications I worked on, the issue is not reducing the friction, it's to increase the friction. Because Indian Railways, if you look around, there's so much dust on that track. It looks like the friction has gone down to almost nothing. So it's very difficult to pull a train with that kind of friction. So there are only two ways I can think about. One is to need to clean the rail in front of the locomotive, and the other is to have more traffic through the same track. Because any dust storm, any wind blows leaves and particles on the rail, and it's slick rail, not a good rail. So the arc which I talked about is used in some of our locomotives in India, but it's mostly sand that's used.
Okay, sir. Sir, next question. A long train is not an integral mass. Sir,
Right.
is that a basic issue in controlling the movement?
Yeah, so as I said, the long train is not an integral mass. So there is, between locomotives, there is coupling. And depending on the type of coupling, it may move an inch. It's a spring with a dash part and a gap. So it moves a few inches or 5 centimeters or so in some of the cars. And some of the intercar cushioning cars, when you transport, what you transport is passenger cars in that train, it needs a lot more cushioning. So some of them move 30 centimeters between trains. So the computers on board the locomotive knows what kind of car it is, what kind of coupler is used, and what kind of forces are expected throughout the train. So we have models. I think I mentioned a rope model. Rope model assumes it's like a rope you can pull but cannot push, and there's a little bit of leeway, and we have so many models running on that train to look at the forces all over the train. It definitely is not an integral mass. It's a distributed mass with couplers and springs in between. It's not a simple problem, but we don't need to solve it exactly, but we want to make sure that the drawbar forces at any point in the train is not too high. So the train won't separate into two, or it won't jackknife.
Okay, so moving on to the next question. India ideal to tie up with India to improve the efficiency of Indian railway system from the present.
I have many ties with the Indian railway systems. I have visited Rail Bhavan. I have visited most of the member electricals. Calcutta, forget Chitra, I think Chittaranjan Locomotive Works. It's near Calcutta. Many factories. We have set up a factory in Bihar to make it, and there are 500 engineers work in India for India operations. So our objective is to, first one, we have an order for 1,000 locomotives, build that. After that, build locomotives in India and ship it elsewhere. That hasn't started it, but that's our plan right now. But I don't know how personally I can help. If there are anybody has a specific questions, like a specific things you need, I can help. Otherwise, most of my help is through the 500 engineers in Bangalore.
Let's go to the next question. In battery operated train, what is the distance covered in a single charge? And what is the time taken to fully charge the batteries?
Okay, it's when you say battery operated train, the whole train itself is not battery operated. If you had to charge by plugging it in and then use it, you cannot make money out of that. The electricity cost is too high to make money. You lose your investment. So these battery train operated locomotives are put in between. So for example, if you have 5 diesel locomotives, you'll replace one and put one of these battery in its place. So when you go into braking, it receives free energy. That's what's used. So there is no charge for electricity. Even then, it's difficult to make money. So even if the electricity is free, battery cost is so high for any private investor to make money out of it. They're looking for money to be returned in 2-3 years. If a government is subsidizing it, it's a different story. So if you want to make money, you need free energy. So that's our first attempt. And there's a ton of free energy coming from a train. Every time it comes to a stop, there is a huge amount of power coming in. So our objective is to store it and then return it back to the train itself to save fuel efficiency. 30% fuel efficiency is what is expected out of putting back on board the train, not replacing all the diesel engines. I don't know if I answered that question or not.
That's clear. We are moving on to the next question. What is your opinion on creating a vacuum inside the locomotive to increase adhesion?
Couldn't follow that question.
Okay, what is your opinion on creating a vacuum inside the locomotive to increase the adhesion?
Oh, create a vacuum. The spaces involved for I'm not talking about a passenger locomotive or a small train. These trains are 2-3 kilometers long trains. It's impractical to make that kind of system. That's what I think it is.
Okay, sir. Then the next question I raised was, can you brief about the braking system in these ultra heavy mining vehicles? Second. Hello, sir.
Yes.
The next question is, can you brief about the braking system in these ultra heavy mining vehicles?
Can I see the questions? There's audio problems.
Okay, this is right in the chat window. Is it visible for you, sir?
No, I don't see anything.
Sir, shall I read for you because I don't have the control. Harindalal, sir?
Yeah,
Can you make the chat visible for him? I am not the host.
I cannot hear you properly.
Sir?
Hello?
Yes, sir. Could you please make the chat visible for him because I'm not the host. so I can't do the necessary things. Will you please, he's not able to hear me.
No, I too cannot do that. I'm sorry.
Yes, and answer is showing that this thing. Ajit sir, is it visible? Ajit sir. Sir, is it visible for you?
Yeah, I can see it, but I don't know what I should be seeing, but I can see something.
Sir, can you brief about the braking system in these ultra heavy mining vehicles?
Okay, in the braking systems on these trains, there are many braking systems in the train. The first and foremost, which is going to be used, is a regenerative braking system, where the traction motors make electricity and get stored in the battery. That's the first priority. The second one is dynamic braking systems, where these traction motors produce electricity and it's dissipated in resistors. The third one is what's called a train brake, which is air brake application on each of the cars. And the fourth one is an independent brake, which is an air brake application on the locomotive itself. I gave it in the order of preference: regen first, dynamic braking second, train braking third, and the independent locomotive braking fourth. The last two are used to stop the train typically. In case of emergency, there's something called an emergency braking, where the whole pressure is released and every car will apply braking. Even then, it takes a long time to stop the train. Since it's not an electric locomotives, they return some of it to the catenary. The ones I work on are not electric. Okay.
That was clear. Then the next question is there an increase in the railway track in the US?
There any what?
Is there an increase in railway tracks in the US?
Grade or grade crossing?
Is there an increase in the railway tracks in the US?
Don't understand the question. So here is what I recommend. I'll share my email address or phone number to anybody who has questions. They can contact me directly. I'll be more than happy to answer any of the questions.
Sir, there is one more question. The last one. Are we good to go with that, or are you sharing them?
Okay. Can you share the most adventurous experience?
Yeah, that one.
That one was in Madhya Pradesh. One of them, I showed you a picture of a tiger. That's from Madhya Pradesh. I went to Pench National Forest in India for part of a technology trip. In between visiting India Rail Bhavan, and in Chennai, there is a power plant, Basin Bridge, I think that's the name of the place, where we were trying to improve the efficiency of the power plant in Chennai. So that was one trip. The other one was in Williams F1. That's a Formula One racing company. There they use flywheels for store energy and pass give you a 6-second boost for the Formula One racing car. I worked on flywheel energy system for New York City. And then we were trying to use whether flywheels could be used in the trains to store energy. And in that connection, I worked with Williams F1 Formula racing cars. So that was a fun experience also. There are lots of fun trips, different trips. Tibet Locomotive is a fun experience. Many. We've been to Israel, to Egypt, to lots of places.
Thank you so much, sir, for sharing your experience. That was our last question. We are almost done with the Q&A section. You have provided us with a trove of information, and we are grateful for the time you have spent with us. Gratitude is the fairest blossom that springs from the soul. So I welcome Ms. Amina Muhammad to share wholehearted gratitude.
Hope I'm audible.
Yeah, you are audible. You are audible.
A warm good evening to one and all. I deem it as my privilege to deliver the word of thanks on this occasion. On behalf of Indus Society Weekly Webinar Series and its collaborators, first and foremost, I extend my heartfelt gratitude to our illustrious speaker, Mr. Ajit Kumar, for taking out time from his busy schedule and for a wonderful session. Thank you, sir, for your valuable time and effort. I also extend my gratitude towards Mr. A.G. Harindralal, sir, who plays a key role in the success of this webinar till date. I'd also like to thank Ms. Rosmi for being the moderator, and IEEE volunteers Ms. Hannah and Alan for their active participation in the smooth conduction of this program. Last but not the least, I would like to thank dear delegates and participants without whom the program would have been incomplete, and for your kind listening and patience throughout the session, and for sharing your views and opinions and making this session a successful one. Once again, thank you, everyone.
Thank you for listening to me. And any questions, let me know. I'll try to answer. I think Harindralal should have my email address, and phone number, everything else. So can contact me.
Sir, the next webinar will be happening next Wednesday, 17th November 2021 from 6 to 7 p.m. It will be our 84th talk section and will be handled by Professor V.S. Jisha, Chair, Robotics Automation Society Kerala Chapter, on the topic Robotics and Society. There is no real ending. It's just a place where you stop the story. You are all welcome to join us on next Wednesday. We look forward to seeing you then. I hereby announce that meeting is officially dispersed. Much thanks to all of you.
Ajit Kumar, a lot of experiences shared. We are thankful to you and coming over here at this odd hour from US to share your wide experience with us. Thank you, Mr. Deep. Thank you very much.
Thanks a lot for inviting me. More than glad to share any experience I have with this group.
We expect more support from you in future programs. Once again, thank you very much and wish you all the best.
Thanks. Bye.
Thank you very much. Thank you very much. I was asking about the rail track situation because the number of the number of rails that have been not increasing in the US, and so you have come up with a way of increasing the lengths of the trains, and that's what you have done. How much more can you go in that route?
Oh, quite a bit more. So with today's technology, you don't need to increase the length of each train, but you can have a conveyor train or a platooning of trains. So you can have one locomotive with, let's say, 20 cars. Behind it, you can have another locomotive with 20 cars, and one could follow the other without an operator. So just like the end of train device could communicate to the head of train device, and one operator could run 10-mile long trains. And we are working on it for something like that for Brazil. So, but Brazil one, they didn't want to go conveyor or a platooning of trains. You can have, with today's technology, you don't need You don't need to worry about intercar forces. Right? All you have to do is a train follow the other one, say 30 meters behind it. You follow?
Do
Same?
do the best you can with what is available on the in terms of the rail tracks, right?
Right. So you can increase the length of the train significantly.
Yeah. Thank you very much.
You're welcome.
I hope to see you for next Wednesday,
Sure.
this time, and another great talk.
Okay. Thanks.
Yeah. Thank you very much. Once again, have a great day, all of you.
You too.
See you next week.
What is the problem you had? I think we had a problem with the Zoom. All kinds of disturbances were there today.
No, only the sound quality of one of the volunteers was less. Otherwise, it was okay.
You know, so many disturbances were coming, so many interferences were coming in the screen also.
No,
Unusual.
it was not. So nothing of that sort. Nothing of that sort. Maybe at your end.
It was coming from Zoom. That's the problem.
No, we did not experience any. We did not. I experienced only the sound quality of the Rosmi was slightly low. I don't know why. Maybe she may be staying in a hostel. Some Wi-Fi problems. Otherwise, it was okay.
I found some announcements and interferences from Zoom about their program and about all those things coming in between.
No, sir, I don't know. I don't know.
Oh, it came today. I don't know why. Maybe that's the reason.
Initially, there was a child talking. Maybe Bobo Umar's grandchild. Maybe I forgot to switch off his mic. That is the only problem I had. Otherwise, it was okay.
Okay, thank you very much. Okay. Okay. Good night.